Sometimes it's easier to break in through the back door. In this episode, we invite special guests Pete Morgan and Aaron Bray to discuss what supply chain attacks are, where we've seen them successfully executed, and why we're going to see a lot more of them in the future. We'll discuss how SUNBURST, the SolarWinds attack ravaging large corporations and the US government, may not have been the quickest or lowest cost attack vector, but it was a stealthy and devastatingly effective attack. I'd like to welcome to the show Aaron Bray and Pete Morgan. Aaron is a co-founder and CEO of Phylum, an application security company. Aaron has spent the last 14 years working in various capacities at the intersection of software engineering and information security. He's spent substantial time in the US intelligence community and has worked extensively on both offensive and defensive applications. Pete Morgan is co-founder and president of Phylum. Pete has been a career security researcher focused on hardware and software reverse engineering. He's led teams at Montesano Security, Akivant Optiv, and Clever Security. Pete, Aaron, welcome to the show.
Thanks for having us.
Thanks for having us.
Well, you guys have some really relevant backgrounds, I think, to some of these supply chain attacks that we've seen. And SolarWinds, I think, in magnitude and its ability to penetrate into the US government is pretty unprecedented. And so a lot of people are talking about these attacks. I'm really excited to dig into all the aspects of what makes up a supply chain attack, what are the different kinds, what are some historical examples, and then kind of what can we expect to see in the future. So I guess let's start out with the basics. What is a supply chain attack, and what kind of different kinds of supply chain attacks are out there?
That's a great question. So supply chain attacks can come in many different forms. There's kind of the traditional physical supply chain attacks, which essentially revolve around gaining physical access to some device in order to be able to subvert it. In addition to that, we've seen some things with firmware or software backdoors where malicious updates or code signing keys are stolen, and essentially what amounts to malicious updates are applied. There's also cases where software and third-party dependencies have been backdoored, which have had ripple effects downstream for applications that consume them. Historically, there have been a variety of different examples. Of course, most recently was SolarWinds, where some malicious updates were applied. Bad source code effectively was added to the build of some of SolarWinds' core libraries, which then got shipped out to customers for consumption. There have been things like Stuxnet, where physical access was used to subvert systems. Of course, ATM malware has been a popular thing in the past, which is sort of similar. There have been a few cases of things like compiler and build toolchain attacks, where the actual software that builds software that's being used has been subverted, as well as things like CCleaner, which was signed by CERT, but the developer was actually compromised. And fairly recently, MageCard, of course, has been on the rise, and they've had a couple cases where they've either compromised third-party software to add things like credit card skimmers. So, for example, British Airways got hit with an attack through that vector. And they've also done things like, fairly recently, they compromised the Twilio SDK through, an attack on their open source an S3 bucket containing their source repository, where they were able to add a backdoor, which, of course, resulted in effectively a malicious package being published to NPM. There's also been a few other cases of open source compromises. So a whole bunch of Ruby gems were taken down fairly recently. And there have been a few cases like EventStream, which were fairly high profile, where developer credentials to publish packages were actually stolen.
Yeah, I mean, these seem like pretty complicated ways of getting into a target. Pete, why would somebody choose to conduct a supply chain attack versus, say, trying to phish an employee or compromise credentials?
It's a great question. So there's a lot of reasons why this is so desirable. If you look at some of the embedded space, having audited hundreds and hundreds of different devices that do this, one of the first things I look for is the firmware update functionality, because I know if I break that and I can control a firmware update to a device, and potentially a lot of devices that run that same code, you lose control of the fleet of those things instantly. So you have one attack that has a massive, massive effect. And fundamentally, the larger the installed user base that's using the software, the larger the attack linearly. And when we look back at SUNBURST, I thought it was really interesting because while the attack was sophisticated, the attackers did not use what effectively would be the lowest cost attack vector to get in. They compromised the build server within the SolarWinds organization, and then were able to inject code after it came out of a version control system and before it actually got built into the final product and signed, which is elegant. But in most of these cases, you see attackers minimizing the equity they burn when they're performing an attack. So if there's a lower cost path that requires them to burn less equity in order to accomplish that attack, they're almost always going to choose that and save the higher equity vulnerabilities and exploits for them for later attacks. So seeing this was interesting because the same exact attack that was used in SUNBURST can be accomplished on just about everybody using a computer today if you just attack open source libraries.
So that's really interesting, Pete. I think modern software is basically the practice of stitching together all these different dependencies to solve problems, right? You don't want to have to write a sorting algorithm every single time that you have a database transaction. Like, you're going to pull in a third-party library that, as far as you know, is well vetted and does what it's supposed to do. Pull that into your code and then use that so that you can go about solving your business problem. So given that that's the state of software engineering today, just how vulnerable are applications to supply chain attacks on open source software?
That's really interesting you bring it up that way. I think it started out with modern software engineering practices with that as the goal. A library being a nice self-contained piece of functionality that was tested and can be used for that function. But what we're actually seeing in the open source world is the blurring of the line of what a library is and the drift into simply using package managers for storing functions for anything. That could be, align a piece of text or, print out something using some fancy colors. And now those are dependencies. And what we're seeing happen is these chains of dependencies have exploded in use.
And the net result of that really is we've seen the average number of dependencies per package grow from single digits to now dozens over the last couple of years. The size of the ecosystem at large is growing at a nearly exponential rate. If we look at NPM by itself, which is, one of dozens of these big software ecosystems, it's grown from about 12,500 packages only 5 years ago to nearly 1.5 million today. And it keeps growing at around a rate of 1,000 net new packages a day on average. And that's not counting updates to existing packages. That's, brand new, never before seen, initially published packages that people are producing. And so the landscape has just shifted very dramatically over the last few years. And what was really maybe a small gap in an organization's security posture a couple of years ago has now become a big issue, especially when you expand that all the way out to the edge. Just like what Pete said, the way that these things have sort of been pushed to, Coderees has sort of been pushed to its logical extreme. Now we see a package like React, which is very large, very popular package. If you look at, what it says on the site on NPM where it's hosted, it self-reports almost no dependencies. But if you take and actually go look at the list of dependencies that are in the project's build, and you take those dependencies and then the dependencies of those dependencies, and you follow that all the way out to the edge of the graph, you end up with nearly 7,000 possible packages, which, honestly is pretty much in line with what we see across the board.
Yeah, it's amazing how much attack surface there is on some of these things. So to follow the thread here, the idea is when we look at SUNBURST, as far as we know, the attackers compromised essentially the build server for Orion, I think was called, right? The network management software. And because they had access to the way that this software is getting built, they were able to put backdoors and special code inside of those packages so that SolarWinds itself became the distribution vector for all of this malware, right? Now, that required, I think, probably some, maybe we'll see, but maybe some sophisticated techniques for compromising that build server. So in some sense, the build server was the front door, right?
Right.
But what you're saying is attackers don't necessarily need to attack a build server directly to get the same kind of reach that the SUNBURST attackers did. What they could do is essentially target the dependencies of the software that SolarWinds in this example is building, and then piggyback through totally legitimate packaging systems to get their code incorporated into the solution. Right? Is that the idea?
That's
Absolutely.
And one of the interesting takeaways from this is, so React is like supported and largely developed by a group of maintainers at Facebook. Spending my life in computer security and application security, attacking Facebook as an individual is a ridiculous endeavor. They hire some of the best security researchers in the world, pay them tons and tons of money, and give them all the time they need to do a great job. That is not a good matchup. But that's not the matchup we're discussing. We're discussing attacking a developer who doesn't know they're being attacked, has no real means of defending themselves, and trying to gain access to this unknown developer on the internet that manages one package, 2 or 3 levels up the dependency tree from React. And if you win that game, now you can inject code into their repository, which will then get filtered down into React and the things that depend on React. So it's really changing the concept of changing the attack focus from institutions that are well defended to individuals that don't know they're being attacked.
So it sounds like you have a number of options when you're attacking an open source package. One would be you try to compromise the credentials of someone who has legitimate commit access, right? So you find them on a password dump, or somebody accidentally commits SSH credentials somewhere, or something's misconfigured and you're able to commit as them, right? I guess other options would be, I'm sure you guys have seen the underhanded C contest, but the idea that you would have code that on first glance looks totally benign, but there's a nefarious purpose to it that's you can trigger if you're clever about it. And it might sound hard to do, but people are pretty smart, and there are some amazing examples of how you're able to do this. And then finally, there's also just good old fashioned typo squatting, right? Is one of these things we talked about. What does that attack vector look like, and how would you do that?
Sure. So typo squatting is super popular because in all this amazing automation, one of the perennial computer science problems pops up, and that's naming. And what the typo squatting attack really is if I'm a typo squatter and Aaron is the person that runs a package, and we'll call it, Aaron's code. And it's a library that does a whole bunch of things that Aaron likes to do. I, as a typo squatter, might download Aaron's code, seeing that lots of people use it, and I might rename it. But instead of Aaron with 2 A's, I might put 1 A. Or I might add an S to the end of it. And basically, I'm trying to exploit the idea that humans don't necessarily remember names perfectly. Sometimes they mistype things. And I could also potentially, pay a friend of mine $20 or $30 to write a blog article documenting about how great this library Aaron code is. But they mistype the name, or they misremember the name in the blog article, thereby directing people to use my fake repository.
I mean, is this theoretical, or have we seen this sort of thing?
This happens all the time across all of the ecosystems. There's around 1,000 packages, ballpark, taken down a year. But one of the difficulties here is that if I'm using PyPy and Python, that has an internal naming scheme and names reserved for packages. And if I'm using something like Debian's apt for package installation, that has a different naming scheme. So does NPM. And none of these things are connected. So Aaron's code in Python might not be present in NPM for JavaScript. So I could also take Aaron's code and then claim to have built a port of it, or a JavaScript version, and then host it on NPM. And the visual similarity of the names might lead a developer to think that this is the same code by the same person. I can just use this because I used it in Python. But in reality, there's nothing connecting them other than the similarity of the names. And that difference is extremely important and subtle and somewhat difficult to police as an individual.
Yeah. And I mean, I know there are a lot of solutions out there for trying to make sure that your dependencies are secure. There's this DevSecOps movement, and A whole other class of problems we haven't even talked about here is legitimate, well-meaning developers accidentally putting vulnerabilities into source code. This happens all the time, right? Like we read about CVEs, common vulnerabilities and exposures where a developer accidentally misuses a crypto library or misconfigures something and subverts the security properties of a system. And so there are packages out there on the internet, on some of these package managers that have vulnerabilities in them, and you shouldn't use that version, right? Because that version has got an issue. We're talking about a whole separate class of problems here, right? Which is intentionally malicious code getting injected into otherwise totally legitimate packages. Like, what is the current state of the art for scanning your dependencies? So I have at Shift5, we like ship software all the time. Like, what are my options if I'm concerned about this problem and I want to try to protect myself against malicious packages and CVEs and things?
Great question. So one of the big problems that we've seen over the last couple of years is that while this landscape has shifted so dramatically, with the number of packages that each project depends on increasing dramatically, the size of the ecosystems overall increasing so dramatically, and the number of transitive dependencies that you could end up getting by installing a single package increasing so dramatically, the sort of state of the industry, state of the art has not really kept pace. There are a lot of companies that sort of play in this sort of package analysis space. They focus a lot on, building a software bill of materials. They focus quite heavily on doing things like telling you a little bit about what they know in terms of your vulnerability posture. But really the crux of it is they're not doing a very good job, because not only are they focused essentially on identifying vulnerabilities for the most part and telling you about commercial license problems and things of that nature, they're also, even in cases where they're trying to go a little beyond that, relying primarily on human capital to police these ecosystems, which obviously is something that just kind of doesn't work. That worked 5 years ago in 2015 when you have 12,500 packages, but it doesn't work today when you have 1,000 net new packages being published a day in one single ecosystem of dozens. And, it will not continue to work into the future as the number of developers being minted and produced for, industry at large vastly continues to exceed the number of security professionals capable of doing code audits.
So, you've got cybersecurity solutions like antivirus, and it might seem pretty obvious that, like, if you need to do continuous scanning, you can take something like an antivirus and just, well, we apply that to computers. Why can't we just apply that to these packages that are coming in? What's the reasoning for why we need a whole new set of products?
That's a great question. So I guess there's two different ways that we should probably answer that question. So first is we have to consider how antivirus products typically work and what threat model they're built to address. They look essentially at file metadata, data within a file, so things like static byte strings, the stuff that you might see come down in YARA rules, that would be like an indicator of compromise. And they also will typically do some dynamic analysis by trying to run whatever binary they're looking at in a sandbox. And the problem with applying that paradigm to software libraries and packages is twofold. So often, most of what you're looking at is simply source code. And, often these products are capable of running scripts in a sandbox to get results. That doesn't really translate very well if you're looking at C#, Java, or C++, where typically these things get run through a compiler first before the thing the AV product would actually be able to look at is produced. So from the AV product's perspective, effectively all you have is a set of text files that may or may not mean anything. The second problem is one of what I'll call code coverage. So in most cases, if I download something malicious, like a malicious attachment from the internet, there's a clear, well-defined entry point where I, as an end user, run this piece of malware. It does whatever it's going to do, and it returns. So from the perspective of the antivirus product, that's a pretty easy thing to reason about. It can try and run this thing from start to finish in a sandbox. It can look at what it does, and it can make inferences about whether it's good or bad based on this behavior. But if I have something like a cryptographic library, there isn't one simple, clear entry point. There are a lot of functions that this library might be exporting, any of which might have a backdoor, any of which might contain malicious functionality. And trying to run this from the perspective of an antivirus product where you have to make convictions within milliseconds so a user won't notice the delay, it just doesn't work. It won't scale. And so really, while antivirus products might be effective in their domains, the threat model that we're trying to address here is completely different.
Yeah. And I mean, another kind of terrifying thing, honestly, is like when we're writing software, and we know that we need a MongoDB attachment, or we need an API that's going to help us with cryptographic primitives. We don't really, as a community, have great ways of selecting packages to use, right? Like you might Google Python crypto API or MongoDB examples, and you might find a Reddit post or a Stack Overflow post that uses some code, and you say, okay, I'm just gonna pull this package in and give it a shot and see what happens. But you're potentially pulling in tens of thousands of lines of code, right, at any given moment. So, I mean, like, what are some do best practices exist for how to select packages? And if not, like, what do we as a community need to start thinking about and building to try to make this less crazy?
Yeah, that's it's interesting because you have to think through. I mean, having done this what feels like thousands of times myself, I want to go connect something to something else or build a new piece of functionality. So I go looking for libraries, or I switch languages. Now I'm going to write something in a different language. And my seminal case personally was I used mechanize in Ruby. And when I went to Python, I said, what is the version of mechanize in Python? And then after some searching, reading Reddit, I stumbled on requests. And when I started using requests, I don't even remember if I looked at it in depth. I just started using it and figuring out, does this API have the functionality I need? Yes? Okay, let's go try it out. Now I go a little bit further and look at things like GitHub issues and how many open pull requests are there? What's the kind of activity of this repository? Is there a ton of outstanding issues? How old are the outstanding issues? There's a lot of analysis you can kind of do visually to get some sort of hunch. But one of the big problems is, say I did that the first time I used requests, and I developed an intuition for, does this seem like a reasonably high quality piece of software to use? I did that once. And then as I learned the API, it became my hammer for doing web things in Python. And because I knew the API and I knew how it worked and it was reliable to me in my usage, I've never looked at it since. So I looked at it once. Now, that package has gone through hundreds, if not thousands of updates since I started using it. So even if it was okay then, that's being updated by someone else that doesn't work for me. I have no, ostensible interaction with or nor influence over to the control of their software build process. So I just keep relying on requests and I keep installing it, and it keeps running fine. But what it's actually doing under the hood, there's just not enough time in the world for me to investigate that for every open source package used.
And I mean, you guys said some commonly used packages like React have 7,000 or more upstream dependencies. I mean, how many? That's just the packages themselves. You also have, for each of those packages, how many people have committed code to those packages. Like it almost becomes, it seems like an almost intractable problem for somebody to write a modern piece of software, keep track of all the dependencies that they're using. Non-trivial software, you might pull in dozens of packages depending on what language you're in. If it's JavaScript, maybe even more. And those have all of these downstream dependencies. So you're talking about tens of thousands of packages probably, and dozens of committers maybe for a lot of those packages. I mean, like, it seems basically impossible to do what you said of, hey, let's go like look at this package on GitHub and see who the committers are and do they have a good reputation, and is this thing being actively maintained? Like, it seems like we probably as a community need to try to do a little bit better. I mean, what directions do you see us going in the future to try to solve this problem?
As an individual, untenable was the right word. It is an untenable problem for individuals to manage this on their own. Even if we did some kind of sample studies. on the average amount of dependencies from some software projects we looked at. And, it's in the hundreds of thousands. Pay to do that one time, to audit all that code one time. You have to start over the next week. It's just completely intractable.
And the problem is actually even worse than what you said, because all 7,000 of those packages, if you go and do create React app or you install React for the first time, you will not get 7,000 packages. You'll get some subset of that 7,000 packages because most package managers use something called semantic versioning, which means that if I have package A that I'm building, and it depends on package B that's hosted on the internet, then usually there will be some range of versions of package B that will satisfy the dependency for my software package A. And so I might get a completely different set of software if I install on one workstation or another workstation, or the CI runner that's actually building the production code that will be shipped out to customers. Because depending on what I have installed already on my system, I may get a different set of packages from the dependencies that I have in my file.
Yeah, I mean, and the state of the art, as it sounds, from when I want to do a scan of my dependencies, is essentially to look at semantic versioning of the packages that I'm pulling in and basically see if there's a CVE that matches that package, right? Or you've got human beings manually trolling through NPM looking for bad packages and then manually reporting those to the NPM security team. Did I get that right? Is that essentially the state of cybersecurity and dependencies?
That is exactly correct.
I mean, it seems to me like if we're going to draw a historical analogy from cybersecurity products that we've seen, for example, in early antivirus versus modern antivirus, or early versions of network intrusion detection systems, we started with something that looks very similar to what dependency scanning solutions look like today, which is basically blacklisting. You have a known bad list, and if it's not in that known bad list, then it must be good. Where we've evolved to today is that we have like fairly sophisticated heuristic models that aren't bulletproof, but that at least raise the bar substantially for attackers to have to try to continue to evade these heuristics as we move along. I mean, do you guys see parallel development being the way of the future for these dependency scanning solutions?
Absolutely. When you look at the sheer volume, there's also a really nice academic paper called The Backstabber's Knife Collection that was done earlier in 2020. And they sampled a lot of the documented malicious code found in a variety of different package manager ecosystems. And it was interesting because there are lots of elegant attacks an attacker could use to synthesize malware in a dependency resolution scheme for a supply chain attack. They're not being used, at least it's not well documented that these attacks are very, very complicated in the wild because they simply don't need to be. As I mentioned earlier about the SUNBURST attacks, it's always interesting when attackers choose to not use the lowest cost attack vector. And what the evidence is showing so far is attackers don't need to use anything complicated because it's comparatively so easy to exploit the existing kind of very in-your-face present attack vectors, such as curling a binary down in a post-install script and then executing it. There's not a lot of effective products for detecting even the low-hanging fruit. So why would attackers try to do something super complicated when the easy stuff still works?
And to add to that, since the targets of most of these attacks through open source malware are often developers themselves, those sorts of things will also enable things like the SolarWinds hack, where developer credentials could lead to a build server compromise, for example. And even worse, repository compromises, critical infrastructure compromises, just about anything you could think of, because effectively most developers have what amounts to, the keys to the kingdom. In many cases, they're able to, commit code up. They're able to make changes to repositories. Most repositories don't really have historical attestation. So, you can amend commits in a repository and effectively rewrite history. So you can add commits in the past.
This is crazy. So what you're saying is essentially like Git is not the blockchain.
Absolutely.
So in other words, it's Git is designed for functionality, not for security, right? So like when I'm committing things, it's so that I can go back and figure out, oh, okay, I had some bug that I introduced and I need to figure out which commit broke it, or I have a workflow with my engineers where they're going to build a feature and then merge it back in. It's built around functionality, but I can go. So you're saying I can go back and amend what history looks like so that it completely obfuscates what the commit. That's insane.
Exactly. So there have even been a few scripts. I can't remember the name of the repository now, but somebody actually wrote a script that would let you draw little pictures in the heat map that GitHub draws underneath a repository by going and effectively changing commit dates in the past.
And that's a very common misconception, is that because Git has a log, we tend to think of it as like a log file that hopefully can't be edited or changed after the fact, but it is nothing of the sort.
Yeah, that's insane. And I mean, is anybody going and looking at these password compromises and figuring out whether developers of open source software are like in these password compromises to figure out like, oh boy, like maybe this dependency needs a little bit of extra scrutiny, or is alternately, I mean, is anybody looking to see whether Git histories are not in fact immutable and that people are going and amending things in suspicious ways?
Nothing you can buy today at the moment. We did some cursory investigation of, given a set of packages, how many developers on average, just to kind of do a case study, show up, how many developers show up in password data breaches. And the numbers are staggering, simply put. We were very surprised. Then thinking about it a little further, developers on average use more internet resources than most other users, right? They go to more websites, they sign up for more accounts, they have more passwords and usernames to manage. So we saw close to a third of the software developers we pulled off these open source ecosystems showing up in password breaches and with very high recency. The problems are very closely linked, unfortunately.
And I mean, it kind of blows my mind that developers would show up in password breaches, because unless there's something really bad going on the service that got compromised, it almost implies that they're using weak passwords. And like the fact that this population of tech savvy people would not be doing simple security measures like using high entropy one-time use passwords or things like that, it's actually kind of terrifying.
Yeah, when we in the security community, we run into a lot of people that are paranoid. Aptly so, because you spend your life breaking into things, hopefully for good. You understand how bad things can go, but when you put yourself in the developer's shoes, they're here to build things, and if they can build them faster and still make them work well, that's a desirable trait. So security really, while it's important to some developers we work with, it's not in the forefront of everyone's mind. And the effects can be catastrophic down the line.
Yeah, and I mean, one of the things I'm most interested in cybersecurity is when you can find a cybersecurity product or control measure that actually also helps operations or helps people to do their job. And it sounds to me like we've talked about a couple of things with dependencies in this episode, but on one hand, you've got this really intractable problem of trying to find vulnerabilities and issues in packages, right? And on the other, there's this issue we're talking about where it's like, hey, I come from Python and I have to write a package in Go, and I need a mental mapping from one package to the other, or I'm using Cassandra or Hadoop or something, and I need an adapter to be able to get into that quickly and do things. And the current state of the art is kind of terrifying, that we're like using Stack Overflow and Reddit as the arbiters of what's a good package for me to pull in. I mean, it strikes me that there's probably an opportunity to bring these things together to say, hey, we've got a really good understanding of what packages are well maintained and have high quality, and there's a lot of activity and scrutiny around. And we've also got a really good idea of whether it itself and its dependencies have vulnerabilities in them based on the heuristic analysis we're doing. And you could almost bring security into the developer's workflow without being sort of like, the state of the art for current solutions is that it's a step in your build pipeline that'll totally break your build. And you're just like, oh God, like, I'm trying to do my job here. Like, why is this breaking? Oh, there's some version of a thing that is compromised. Like, now I've got to go back and completely redo this whole section of code because I can't use this package. That's insane,
Absolutely. And, honestly, that is a problem that we've been working very hard over the last several months to solve. So, not only trying to identify these issues before they become issues in a way that will continue to scale as time goes forward, but, also being able to provide recommendations and better fit into the early stages of development rather than simply being a check-in and build step.
That's been something that's very eye-opening, is as we've been peeling this onion of a problem, the amount of information that's out there that can be analyzed is really significant. It's gigantic. I mean, for open source packages, we have not only the source code, but we have the full development timeline of the source code. We can look at all of the people that at least Git will tell us about how they contributed to the code. And when you compare the supply chain security of open source software versus something like malware, we have a huge advantage when looking at open source security because there's a lot more data to investigate. When you're looking at malware, you have to be able to pull apart a binary and draw conclusions from a bunch of low-value indicators to try to figure out is this malicious or not. And that's why a lot of those cases have kind of back-ended with just run it and see what it does in the sandbox. Because malware developers are getting better and better at obfuscating and hiding what the true intention of the software is. With the open source side, we have all of this information. We have GitHub that has issues and they have discussions and all of the information about how this evolved over time that can be analyzed and brought together to give, definitely some more guidance around the security posture of it. But also, is this just a good piece of software to use?
Yeah. And I mean, I think we are seeing hundreds of, quote unquote, compromises of NPM and Ruby gems and PyPy because people are looking at packages for like totally egregious low hanging fruit and typo squatting manually. I bet there are lots of other compromises like SolarWinds, SUNBURST out there that we just don't know about because we aren't looking hard enough. And there are millions and millions of packages, literally millions of packages out there. So I'm kind of terrified that we're going to see a lot more compromises come out over the next 1 to 2 years. Do you guys have any predictions about where we might see some of those compromises and what some of the biggest ecosystem offenders are going to be?
Definitely. Just before we jump into that, I think you're dead on that there's going to be a lot more of this happening. And really the difference there being there's going to be a lot more identified of this happening. It's a perfectly ripe playing field for attack. And when you look at how attackers have operated in the past, there was this entire market for identifying vulnerabilities in major pieces of software and then building an exploit to take advantage of that vulnerability and then selling it. And this happened with certain countries around the world as nation state operators. This happened with crime groups. There's an entire market on kind of the dark web for selling and trading these type of equities. And it's gotten very, very complex. It's very tough. And I think, so like the iPhone, iOS, I think a remote jailbreak sells for somewhere around $2 million right now. If you have the capability to trigger a remote jailbreak, especially without user interaction, you can sell that for $2 million right now. It's a very hard target. But this playground is so easy to do it comparatively. Attackers are just, if they haven't moved there, they're going.
And, as you mentioned, I think the ball's already there because in many cases, these sort of low-hanging fruit malicious packages that are being identified through manual effort, in most cases are up for years before they're discovered, even with, some companies spending tens of millions of dollars a year on R&D to effectively have people go out and look for bad things. I think really the long and short of it is something needs to change and, we need a new approach.
Yeah, it's amazing. I mean, as a cybersecurity professional, it's extremely exciting that there are these new frontiers of cybersecurity that keep opening up and keep the field really fresh. But as a software engineer and an entrepreneur, it's also terrifying because so much of the code that we ship to our customers is third party dependencies. So I guess I should say, if any customers are listening, that we have a pilot going with Phylum, so that they can help us to avoid some of these devastating problems. Yeah, I mean, thanks guys for coming on the podcast. It's been awesome to talk about this really interesting and new problem. Where can interested people learn more about you and Phylum?
Sure. We have a website at phylum.io. That's phylum.io. And we also have a blog on our website as well that we'll be releasing a lot of content on as we go forward.
Awesome. Well, thanks again for coming on the show. Hope to have you on again soon.
Thanks for having us.
Thanks, Josh.
Thank you for listening to this episode of Planes, Trains, and Tanks. If you enjoyed this episode, please consider leaving us a review. To learn more about Shift5 and our products, visit our website at shift5.io or follow us on LinkedIn and Twitter.